Maayong buntag sa tanan. Thank you for attending this online conference hosted by ASEP. This presentation is about demystifying transfer forces and load path with design examples from NYC iconic steel structures. This is the outline of my presentation for today, and since our time is limited, each topic will be discussed briefly. One of the gray areas between member design and connection design is determining transfer forces and understanding load paths. Transfer force is defined by AISC as a force that must be transferred from one element to another through connection elements and whose magnitude and direction cannot be ascertained from maximum member forces. In simple terms, transfer forces are loads traveling between members through the connections with a continuous load path. To achieve accurate and economical steel connections, the EOR must communicate properly the transfer forces and intended load path to the connection engineer. Now, unlike simple structures, the load paths for complex structures are not easily known, and dealing with multiple load cases further complicates the design process. But no matter how complex the structures are, the basic rule remains the same. That is, to have a load path that is continuous and complete between elements in a structure. In this presentation, load path for some of the most complex connections from iconic steel structures in New York City will be demystified. The main objective is to determine the design forces to be used in designing connections. The engineer of record, or EOR, is required by the code to provide sufficient load information to complete the connection design. To satisfy this requirement, two possible methods can be used. In the first method, the EOR can provide a matrix of statically consistent load combinations that can be utilized to determine the required transfer force. An example is shown on the left picture, where joint equilibrium is always provided for each load case. As a result, the most economical connection can be designed since the load path is very clear and all forces are given. However, due to a large volume of data the connection engineer must process, there is a high likelihood of poor quality control. Also, the calculations to extract the transfer force is delegated, which is historically the responsibility of the EOR. In the second method, the EOR provides maximum actual forces, tension or compression, which is a common practice for delegated connection design projects in the US. But the required transfer force is most of the time not provided by the EOR. An example is shown on the right picture, where the forces given are envelope forces that are not statically consistent. This method removes the burden from the connection engineer with the transfer of labor from the EOR. However, understanding the EOR's intent and requirements is greatly diminished. This results into more conservative design of connections. Lateral forces, wind or seismic, acting on a structure, travel through the diaphragm or horizontal bracing system towards the vertical bracing system. If a diaphragm is utilized, the forces transfer to the collector beams using studs for composite floor and deck welds or screws for metal deck floor. This slide shows a sample hand calculation of a simple structure that was presented by Bo Doswell in AS Engineering Journal in 2010. As shown on the left frame elevation, 50 kips lateral load is applied at level 3, distributed uniformly along the 50-foot long diaphragm. At level 2, 40 kips is applied that is distributed equally at each end of the beam. That's 10 kips each, with horizontal bracing. On the right frame elevation, transfer forces and actual loads in the beams are shown, which are calculated using simple statics. This example clearly shows that the actual load in the beam is not a good indicator of the transfer force. Now at level 2, the actual load in the beam is 80 kips on one side of the column and 10 kips on the other side. But the transfer force is only 20 kips. In this case, using the largest axial load instead of the transfer force would be conservative. Now, the transfer force will be 0 at column lines 1 and 3. So it will be very conservative to design the connections for the axial member force. Now, it is important to note that the transfer mechanism dictates the magnitude of load in the beam-to-column connections. Let's discuss some connection design examples for vertical bracing, horizontal bracing, and truss connections. For a vertical bracing connection, there are a number of methods in determining the force distribution at the gusset-to-beam, gusset-to-column, and beam-to-column interface. But in this presentation, only two commonly used methods will be discussed. First method is the KSS method, which stands for Keep It Simple Stupid, and was extensively used in the past. Now, as the name implies, the method is simple and easy to use. Although for most cases it gives an economical design, the method is actually infallible. The second method is called the Uniform Force Method, or UFM. This method provides a standardized means to come up with economical vertical bracing connections with statically admissible force distributions. The vertical bracing connection shown on this slide is taken from the 181 Mercer project for the New York University and NYC. This vertical brace to column web connection with extended plates was designed using UFM. As shown in the force distribution diagram, the brace force is transferred to the gusset to beam interface and the gusset to column interface. Since the gusset to beam interface is more rigid, a moment M sub B is introduced. For this configuration, E sub C is normally assumed as the distance from the column web's face to the first bolt column. Now this produces eccentric moments M1 and M2 at the center of the bolts, which are resisted by the bolted connection in the gusset and beam. To maintain equilibrium, the horizontal component at the gusset to column interface, H sub C, is transferred into the beam connection. In the same manner, the vertical component at the gusset to beam interface, its V sub B, is algebraically added to the beam reaction, R sub B. If the transfer force from the adjacent bay exists, it should be added to HC to design the beam-to-column connection. It is important to note that the beam axial force is internal to the beam member and not necessarily transferred to the beam-to-column connection. However, with the absence of transfer force from most of the EOR drawings, this member force is conservatively assumed to design the beam connections in addition to H sub C. The vertical bracing connection shown in this slide is from 270 Park Avenue project. It's a behemoth structure in NYC with steel tonnage of approximately 100,000 tons. The brace force of this connection ranges from 2,000 kips to 3,500 kips in W14 sections. With this amount of load, it is uneconomical to use a typical welded connection at the gusset to beam interface with either a clip angle or an end plate for the beam end connection. With that, a continuous gusset plate is utilized to come up with a more economical connection. With this configuration, KISS method gives a more workable force distribution, which is used in designing this connection. As shown in the force distribution diagram, the entire vertical component of the brace force, V, is transferred to the column through the gusset to column connection. Similarly, the entire horizontal brace component, H, is transferred to the beam through the beam splice connection. Now, to satisfy equilibrium, M sub 1 moment is introduced at the gusset to column interface. With inflection point at the column face, the bolted splice connection on the beam web is designed for the eccentricity. If the transfer force T sub F or TF from the adjacent bay exists, it should be added to H to design the beam flange plate splice connection. For typical horizontal bracing connections, the components of brace force are transferred directly into the beam through the gusset to girder interface. This is illustrated in the horizontal bracing connection shown on this slide. It's taken from the same 270 Park Avenue project. Since the loads given by the EOR are maximum member forces, the system will not be in equilibrium. As a result, the exact transfer forces from the gusset above the girder to the gusset below cannot be determined. Now the table shows the calculated apparent transfer forces for assumed combination of force directions. The transfer forces for the first two combinations seem reasonable. However, the forces for the last two combinations are conservative with assumptions that are potentially erroneous. In order to minimize the welds required to deliver these conservative forces, the girder web is slotted to receive the continuous gusset plate. As a result, the stresses at the gusset to girder web interface are resisted internally by the gusset plate in lieu of the welds. Now the welds, however, are simply designed for the required shear flow along the girder. The truss connection shown on this slide, also from 270 Park Avenue project, which in addition to resisting lateral loads from horizontal bracings, it also transfers vertical force due to gravity floor load. With maximum member forces given, it is unlikely that exact transfer forces can be determined, since it is impossible to satisfy equilibrium. In addition, assumptions are made regarding the direction of the given loads to calculate the vertical transfer force to be delivered from the gusset to the cord. The table shows the calculated apparent transfer forces for different combinations of force directions. The results are excessive, which could be on the order of 5 times the actual required transfer forces. Now, designing a typical welded to gusset to cord connection would be very expensive considering the possibility of using a CJP weld, and you might end up reinforcing the cord member. Now, given the potentially erroneous assumptions, a continuous gusset plate with welded flange plate forming a built-up cord section is designed for this one. This connection is a more economical solution that is easy to fabricate. Now, as a result, the stresses along section AA interface are resisted internally by the gusset plate in lieu of the welds. The welds on the flange plate forming the cord built-up section are simply designed for the required shear flow along the cord. In conclusion, let me give you these takeaways. First, to design connections accurately and economically, transfer forces must be communicated to the connection engineer by the EOR. Second, there are 4 examples provided to show how transfer forces are calculated and how forces are distributed using a continuous load path that is directly affected by the connection configuration. And lastly, the magnitude and direction of transfer forces cannot be ascertained using the maximum member end forces. With that, I would say thank you for listening to my presentation.